Hello, in this video I'm going to show you how to generate a bell sound using Max MSP just by mixing a few sound waves together. This is something called additive synthesis. We are taking a few basic sounds, we are figuring out the relationships between combinations of them, and we are using that to synthesize complex sounds, in this case a sound that approximates something in real life. The algorithm I'm going to use was created by Jean-Claude Risset, a pioneer of computer music. So we are going to look at his book, we are going to look at his catalog, and we are going to implement his ideas using modern techniques. Let's get into it. Alright, I'm going to start with the same objects I usually start with in patches that deal with sound. Live.gain tilde for volume control, limit tilde with the argument 2 for peak limiting, and EasyDAC tilde for actually getting the signal to my headphones or speakers. Now, if I want to just play a bell sound, I can download a sample and play it, or I can record it myself. And if I really want to synthesize a specific bell sound, I can analyze the sound for its sinusoidal components, for its sine wave components, and figure out how to reconstruct it using Max. But now this time I want to do something else. I want to look at a recipe from somewhere else, an old recipe, and recreate that specific recipe using the modern Max MSP tools. And by recipe, I'm referring to this awesome catalog, an introductory catalog of computer synthesized sounds, it is called. It's made by Jean-Claude Risset. He was an amazing composer. He was one of the pioneers of electronic music and especially computer music. So he has a lot of awesome works using computer synthesized sounds and algorithms designed and executed in a computer. I'm not going to tell you to pause the video and listen to his works, but if you haven't yet in your life, and if you're interested in this stuff so much that you're watching this video, after watching this video, do check out some of his works. I especially recommend Mutations, composed by him in 1969, I believe, which happens to be the same year in which he released this awesome catalog. Now, in this catalog, he describes some sounds he created using Music V, a program to synthesize sound, a very old program by now, and it contains 25 examples of instructions for creating such sounds and his reasoning for how and why he created them. I'm going to put a link to this in the video description. This is on Internet Archive, but today I'm just going to focus on number 430. Maybe down the line I might make some other videos where I recreate some of the other recipes. If you want, you can of course look at these and see if you can wrap your head around some of these recipes and create them in Max. But as I've said, I'm going to focus on number 430, which is entitled 3 Successive Approximations to a Bell Sound. So not really bell sounds, but approximations of bell sounds, but those are damn good approximations. Now that would be, and look at all these beautiful diagrams as we are scrolling through, that would be page 79 if my notes are correct. My notes are incorrect, it would be page 78. Alright, anyway, here in number 430 he describes the 3 successive approximations of a bell sound. And there are some details about the note cards and so on, things that we don't really use anymore. So I'm going to skip to this specific paragraph. This is where things start getting interesting. So here he describes that the frequencies of the components do not form a harmonic series, however, they are not arbitrarily in harmonic, right? And he's talking about the frequency components, the frequency of the sine waves that make up the sound. And he says that, well, they're not harmonic, so they are not integer multiples of a specific fundamental frequency, but they're not arbitrarily in harmonic, as in they're not just random multiples. It's not the fundamental frequency times 42.18 or something. And he goes on, in most actual bells, it's attempted to approximate the following ratios for the first 5 components, right? 0.51, 1.2, 1.52. And what does he mean by this? Well, if I have an arbitrary fundamental frequency, right, to figure out the components of the sound, well, I can multiply it by 0.5, and then I can multiply it also by 1, and I can multiply it by 1.2, and I can multiply it by 1.5, and I can multiply it by 2, and I would get 5 different frequencies, 5 different sounds from 5 different oscillators, and they could come together theoretically to sound like a bell. Right, and then he says here the frequency ratios of the components are as follows, and he gives slightly different numbers. So 0.56, 0.92, 1.19, 1.71, 2, and so on and so on and so on. And here he lists, let's see, 3, 6, 7, 8, 9 components, and we could start with that. Now, what's important is that his frequency ratios are not these, or it's not the boring semi-integer relationships to a fundamental frequency, but they're nudged a bit. Instead of 0.5, it's 0.56. Instead of 1, it's 0.92. Instead of 1.2, it's 1.19. And that is something we are going to try and emulate in a second. And then he goes on to describe the 3 different attempts, the 3 different sounds he gets. And the first one is, of course, the most basic one. And he says in the first sound, all these frequency components decay synchronously, right? So they have the same duration, they have the same amplitude envelope, and this gives an unnatural sound. And then he goes on with the other sounds, but let's just try to recreate this before we build on it and move on to the second and the third sounds. In fact, let's start with a zeroed sound. Let's just take these boring integers and make a very boring sound to figure out the basics of what we want to do. All right, so going back into Max, if I want to make a sine wave, I can use cycle tilde, right? That's the quintessential sine wave oscillator in Max. And if I want to have 9 of these, I can copy this 9 times. It's a lot of work to copy these, so I'm going to cut some corners and copy it in groups of 3. There we go. And it's perfectly valid to calculate the frequencies of all of these, send those to the first inlets, take the signal that comes out and, multiply it by something, add an ADSR envelope, and so on. This could work. It has worked this way for a long time in the history of Max, but nowadays, I do prefer to use multi-channel objects, right? So there are a lot of objects that are multi-channel objects, so they are based on these MSP objects, all these objects in Max that end with the tilde sign. And to access these objects, we have to type mc dot, the name of the object, right? So mc.cycle is a multi-channel sine wave oscillator, and I can tell this object with the attribute chance9 to create a multi-channel signal containing 9 signals in it. So this essentially is 9 instances of cycle. These two are the same thing, right? It's like, imagine if I took these, if I packed these together, if I put these into a single object, it would be this. Now the advantage of this is that I can just change the number of channels dynamically. Changing the number of channels restarts the audio, so I don't want to do this while I'm working. While I'm performing with this patch, but as I'm developing it, I can choose how many channels I'm going to have myself. So I'm going to prefer a multi-channel approach here. I think it's more fun, I think it's more interesting, and I'm going to create 9 oscillators. 9 sine wave oscillators. Okay, well, what did Risset say? Oh, okay, we're going to take an arbitrary fundamental frequency and then we're going to multiply it by these numbers. But again, I don't want to just punch in these numbers by hand. I want to be able to generate a sequence of numbers that are going to be multiplied by a fundamental frequency, right? So I want to have this number box, F for floating number box, and I want to be able to type in 220 here, and then I get, 110, 220, 330, 440, 550, and so on, going into to the different channels of my mc.cycle object. So here's how I'm going to do this. I'm going to create a sig tilde object. Well, I'm going to create an mc.sig tilde object with the attribute chance9. Now, when I send this here, and when I send this number, what is going to happen is that I'm going to get a multi-channel signal where all of the 9 channels contain this specific number. All right, and then I'm going to generate some kind of sequence. I'll show you how to do that in a second. But when I get that, I will multiply the signal containing my fundamental frequency with the signal containing the frequency ratios for each channel, right? And the mc.asterisk tilde, and these names are going to get crazier and crazier, trust me, this object is going to perform multiplication between 2 multi-channel signals. All right, so how do we create these kinds of sequences in multi-channel signals? And this is a core skill, if you ask me, if you really want to work with multi-channel objects in Max. I'm going to create another mc.sig tilde. I'm again going to give it the attribute chance9, but I'm not going to send it any float number, any numbers as an input. Instead, I'm going to type in a very specific message called increments 0.5, 0.5, and I'm going to send it here to this object right here. All right, so why am I doing this? What does this mean? Well, this message is something specific for multi-channel objects that generate signals. And it means that increment some values for me. Increment values going from one channel to the other. I want each channel's value to be an increment of a previous channel's value. And increment things by 0.5. Add 0.5 each time you increment and start from 0.5, right? So if I do this, I'm going to get a multi-channel signal where the first channel is going to be 0.5, the second one is going to be that plus 0.51, the third one is going to be that plus 0.5, 1.5, and so on and so on. In fact, we can visualize this using mc.number tilde. If I type this in here, let's type the name here for accessibility. There we go. If I turn my audio on, I can send this message, and then I can look at the values of the different channels, and you can see it is incrementing by 0.5. These kinds of objects, if you click on them and go to their reference, do contain other messages that do similar generations of values across multi-channels. This could be interesting for exploring different applications of such an algorithm, but I will leave that to you. Right now I'm going to go back to my values. Now, you will notice, all right, well, here Risset says 0.51, 1.2, 1.5, 2, and I'm kind of cutting corners here by just incrementing everything by 0.5, but I hope you will forgive me for cutting these corners. In any case, if I take this signal and if I multiply my fundamental frequency with this, I'm going to get 9 channels as a result, where each channel contains a frequency value that is a fundamental frequency times the frequency ratio. Let's write these two. Fundamental fric, of course short for frequency, and frequency ratio. Beautiful. All right, so what is going to happen if I plug this into MC cycle? Well, first of all, I don't need this at chance 9 anymore because this multi-channel object is receiving a multi-channel signal. So it knows how many instances of cycle it should contain. It's receiving a multi-channel signal with 9 channels in it. So of course it's going to have 9 instances of cycle in it. And when it receives this information in its first inlet, it's going to generate a bunch of sine waves, each corresponding to one of these frequencies. All right, beautiful. And if we want to generate these sounds over time instead of like this constant klaxon that just does not end and makes you rip your ears out, we should also consider adding an amplitude envelope. And I'm going to do this in this case through the mc.adsr tilde object. ADSR is of course the standard description for an amplitude envelope, how a sound's amplitude is going to evolve over time. And I'm going to give this some arguments, right? If I give it some arguments, all the channels are going to behave the same way. All instances of ADSR in mc.adsr are going to behave the same way. So attack in milliseconds, let's make this very short, 5 millisecond attack, very quick. Decay, let's make it happen over 100 milliseconds. Sustain is not an amount of time, it's an amount of amplitude. So 0.8 instead of 1, be a bit more quiet. And then release is how long it takes for the sound to go back to 0, go back to an amplitude of 0, to release, so to speak. And let's make this really long, like 4 seconds, 4,000. All right, and I'm going to give this some extra attributes to make it work the way I want it to work. Max sustain at max sustain is going to be 0. So when I trigger an envelope, I don't need to send it another message to turn it off. It's just going to trigger the entire envelope without sustaining. And then at legato 1 is going to enable legato, meaning that if I re-trigger the envelope before it's over, instead of snapping back to the beginning and probably generating some clicks, it's instead going to start from where it is and then take that as a starting point of the attack of the envelope. All right, and if I have everything right, I need to send this guy a message of 1 to its first inlet for it to trigger the envelope. Oh yeah, of course, I have to also tell it how many channels it should have. So at chance 9. And the resulting envelope should always be multiplied with the signal on which we are applying this envelope. So mc.asterisk tilde, the audio signal from mc.cycle goes here, the envelope goes in here. And now for the result, well, live.gain expects a regular signal, a regular audio signal, and I'm getting multi-channel signals here, and these have 9 channels, so I can't really just cram it into my stereo signal. Well, I can, but it's probably going to sound horrible. So I'm going to use mc.mixdown tilde with the argument 2. I'm also going to give this guy the attributes auto gain 1. What does this do? It takes the multi-channel signal, it mixes it down to a multi-channel signal of 2. So it's just a 2-channel signal, a stereo signal, and auto gain 1 ensures that their amplitudes, their volume, their gain are scaled down appropriately, so it's not all the sounds at the same time crammed through 2 signals, but it's like we are mixing things down to 2 signals. And if I want, I can use mc.unpack tilde with the argument 2 to unpack this into 2 nice, lonely, single, non-multi-channel audio signals. Alright, so my audio is on, my gain is normal. Now if I click this, I should hear a sound that will probably not be too exciting. Beautiful. Okay, this kind of sounds like an approximation of a bell. It's like the old-timey video game version of a bell. Right, so it's not incredibly interesting, but it's a start. So this is the sound we are going to craft into a bell sound. This is more or less the first sound, or the 0th sound Risset was describing here. So let's go back here and let's see what Risset did with this information. So he changed the frequency ratios to, he gave the frequency ratios a slight random offset, right? And this is what he means by arbitrarily, not arbitrarily in harmonic. This is arbitrarily in harmonic would mean completely random values, completely random frequency ratios. Well, not arbitrarily in harmonic would means I take the logical frequency ratios and I nudge them a bit so they're a bit off, right? And this is going to create a really cool effect on the sound, as we are going to see. But to be able to see this, we have to ask ourselves, well, how do we nudge the frequency ratio? How do I take these values that come out of, let's turn the audio off as we are working with these signals. How do I take this output? Actually, let's turn it back on while we are working with, when we are looking at these values from the MC number tilde objects. Anyway, let's get back on the track. How do I take these numbers and I nudge them slightly in a way? Now, there's a way I can generate random numbers very easily in multi-channel signals, and that is again through using the mc.sig object. I'm going to send it another value. Instead of increment, I'm going to send it another value that will result in it generating, a bunch of random numbers for each of my multi-channel elements. How am I going to do this? I'm going to go to the reference, let's see, and I'm going to use the message random range, generate a range of random values. The random range message generates a uniformly distributed random range of values for all channels between the first argument and the second argument. In my opinion, this is not worded very well, kind of implies that the arguments define which channels get random numbers, but it's actually the range of the random generation. So what this means is if I send mc.sig the message random range and then let's say -1 and +1, I should get, let's see, a result where each of the channels have a uniquely random value between -1 and +1. And I can send it the message again and again and again to generate this. Right, so for instance, well, what do I want? My first frequency ratio is 0.5 and I want to add to this something like -0.2, and 0.5 plus -0.2 is going to be something like, I don't know, 0.3 or something, right? And we can actually calculate this instead of me trying to randomly do this in my head. So let's combine these two signals. Let's add their values together. I can use the mc.plus tilde object for this. mc.plus tilde, add two multi-channel signals together. So this and this, my frequency ratio plus my frequency ratio offsets. And the result would indeed be what I want. 0.2 something something. And the second frequency ratio 1 plus 0.09. So the result is 1.09. So there's always this slight nudging of values. Right? And I can take this result, and this result, let's delete these number boxes, and this result could be the frequency, the offsetted frequency ratio with which we multiply the fundamental frequency for each instance of our channels in our 9 multi-channel signal. All right, well, how is this going to sound? Much better. Look at this. This is just a beautiful sound. Amazing. And I can click this random range to change the makeup of the random values again. And if I click this, the ratio is going to be a bit different. And if you really want, you can turn this into a parameter, right? I can take these random values and I can multiply them with a scalar value, uniform value across all the channels in order to change the effectiveness of this offset. So let's see, mc.asterisk tilde multiply a multi-channel signal, in this case not with another multi-channel signal but with a plain old float number. So if I multiply my random signal with 0.1, its effect is going to be much less severe. It's going to be 1/10 of what it was before. And this would work the other way around, right? If I kind of increase this value, if I like multiply this by 20, then I'm going to get this very, very severely inharmonic sound, which is also beautiful. This is a beautiful sound to me. There we go. Like these are all beautiful sounds. One thing I should watch out for is that if this number is very high, right? So let's say something like 151, and then I'm multiplying this by that, and let's say one of my random values is -1, so I'm subtracting 151 from my fundamental frequency, and there is a danger that this lands me at a frequency ratio that's negative, and I really don't want that. So I should always make sure that whatever I get as my frequency, I should use the mc.abs tilde object on it, which is going to make sure that the negatives turn into positives. That's what an absolute value is. This is going to make sure that the negative values turn into positive. They're positive counterparts, so we are not going to have any negative values to deal with as we improve on this algorithm. Okay, that's a horrible sound. Apologies for that. Let's fix this. If I multiply it by 20, beautiful. Now this is the kind of sounds I want. Okay, now Risset indeed says that, well, in the first sound, all these frequency components decay synchronously. This is where we are at right now, and this gives it an unnatural sound. And again, this is a beautiful sound. It's much better than what we had before. But I completely agree with Risset that it's not natural. You could not fool me that this is a real bell, a real church bell, a real bell I'm hearing. And if you really want to, you can stop here and you have a nice synthesized old school bell sound that you can play around with. But let's see how Risset developed on this. So he says in the second sound, the components have a decay time approximately inversely proportional to their frequencies. And then he says this thing in a parenthesis that I'm going to skip over. This principle is violated in one instance where a lower component decays faster. I'm not very interested in that right now. Right, I'm interested in this aspect, the fact that the components have a decay time approximately inversely proportional to their frequencies. What does that mean? Well, until now, the amplitude envelope we are using is fixed for all the sounds. They all have the same release, right? Risset is calling it decay. I will refer to the release of the sound here. They all release over 4 seconds, but Risset implements a version where the higher the frequency is, the lower the release time is. So the lower frequencies ring out longer while the higher frequencies ring out shorter, and this creates a better approximation of a bell sound. So how are we going to implement this? How are we going to figure out the inversely proportional ratio of the frequencies? Well, it's not too difficult. One way of achieving this could be through, let's see, taking our frequencies here and dividing them by the fundamental frequency. Wait, no, the other way around. Taking our fundamental frequency and dividing for each channel the actual frequency we are hearing. This should give us a number that is inversely proportional, right? So the number is going to be lower the higher the frequency is, if I have this right. And I believe this is where I'm going to have the weirdest object name ever. It's going to be mc.!/tilde. And if you already know what this is, congratulations, you are a max MSP nerd. I'm very happy for you. I'm going to send you a medal to your post box. But I think I should explain this here to make sure that things are understood well. So slash is the division object, right? So if I say /5, well, this is divide whatever's coming into the first inlet by 5. Like if 10 goes in there, 10 divided by 5, I would get 2. All right. Well, what about this guy? Exclamation mark tilde. It says divide input from a number, right? So here, instead of the incoming number being divided by the argument is divided by the incoming number, right? So it's reverse. So now whatever comes in here, the operation is going to be 5 divided by that number, and we are going to get that result. So if I send in 10 here, I'm going to get 5 divided by 10, which is 0.5, right? Or if I send in, I don't know, if my argument is 10, and if I send in 2, well, 10 divided by 2 is 5, and so on, right? And this is a small difference, but these kinds of operations make this kind of view object really useful. All right, and then I want to do this on signals, so I'm going to add this tilde at the end, and I want this to happen on multi-channel signals, so I will type in MC dot, and this is how we have our very, very, very strange object name, MC dot exclamation mark slash tilde. It's like someone is swearing to me in a language I don't know, but I don't think that's the case. I don't think I've upset MaxMSP enough that it starts swearing at me. Anyway, to the right hand, I'm going to send my fundamental frequency, and to the left hand, I'm going to send my frequencies. So my 9 frequencies as a multi-channel signal. All right, so the result should be, ideally, a number that is inversely proportional to the frequency, and let's see what comes out. Okay, so the first one is 0.8, the second one is 0.6, the third one is 0.4, 0.5, 0.4, 4.3, 0.2, and so on and so on. So more or less, it is inversely proportional. The later the channel is, which is the higher the frequency, the lower this value is. And this is going to be the case no matter what my fundamental frequency is, and no matter how, in which way I randomly offset the frequency ratio. It is always going to go down like this, meaning I can use this as a value for the release, and the last inlet of the ADSR tilde object is for setting the release. And guess what? If I send this guy a multi-channel signal, well, then it's going to make sure that each instance of my amplitude envelope is going to have that specific release. Now, of course, I don't want to have a release of 6 milliseconds or 1 millisecond or 0.3 milliseconds. I think that's not going to sound good at all. So I should multiply this by a number. And maybe I'm going to start by multiplying this number by 4,000. So MC.asterisk tilde 4,000. So whatever comes in here, multiplied by 4,000. And I believe now that I've given it this input, I don't need this chance9 attribute anymore. Because MC.ADSR is going to know that it is receiving a 9-channel multi-channel signal, so it should have 9 instances of it, and it should send out a 9-channel multi-channel signal. All right, well, how is this going to sound? Let's find out. I'm very curious myself. Oh, beautiful. And we can hear lower frequencies ringing. Look at this. Now it's much more bell-like. It's not perfect yet, but it's really much more bell-like. Let's give it a slightly stronger frequency ratio offset. Let's lower the frequency a bit, and let's hear it again. Ah, no, this is music to my ears. This is the kind of bell sound that fascinated composers in the 50s, 60s, 70s, all the way up to 2020s, if you could believe it. Just a beautiful sound. All right, and yeah, so this is the second sound Risset describes, so he does not stop there. He does say that the sound is much more natural, yet still a little dull. All right, so we are getting there. I mean, this is a cool sound, right? At least to me, this is a cool sound. It's much more bell-like. We've designed a cool sound here, but there's one more step we can take according to Risset. And he says, okay, in the third sound, this is the final version. This is the ultimate. This is the I forgot the Greek letter, the omega, I believe. Alpha would be the first. Yeah, the omega. This is the omega of bell sounds in this specific recipe. And he says in the third sound, each of the 2 lowest partials is split into 2 components of slightly different frequencies. So 224 and 225 368 and 369.7. This causes beats which add some life and warmth to the sound. And indeed, if you take two frequencies that are slightly different from each other, like really like a difference of 1 hertz or a difference of 0.5 hertz, it is going to cause these periodic variations, oscillations of amplitude, which we call beats. A really cool effect. And he says, yeah, it's likely that in real life, Bell's partials are split into two close components due to departure from rotational symmetry. All right, well, let's not think about that too much. That just goes into the world of physical modeling. But it is a good motivation for what he's doing. And I'm going to interpret this in a slightly different way. To create a really fat sound, I want to not apply this to the two lowest partials, but I want to apply this to all of the partials, right? So I want to do something tricky where I take the frequencies that go into MC.cycle, copy them, give each of them a slight offset, and play them as well, right? Again, this is more tricky than you think. I want to take all these frequencies. I want to take 9 frequencies, or nine numbers representing the frequency. I want to copy them. I want to nudge them a bit, very much like how I nudged the frequency ratio here. And I want to combine those together, not add them up, but combine them so I have a multi-channel signal of 18 channels and play them together, which should create these awesome beats between the notes, between the frequencies that we are hearing. All right, so how are we going to do that? Well, the nudging part is easy, right? We already have our offset algorithm here, so I can just copy this. Random range -1 to 1 goes into MC.sig. We still want 9 channels. We are offsetting 9 channels, and then we can multiply it by a scalar amount, a single number, to be applied on each channel in our multi-channel signal. And this would be the frequency copy offset, as I'm calling it. All right, so I can take another instance of my frequencies, right? So whatever's coming out of MC.abs, the numbers representing the frequencies. And I can use MC.plus tilde to add this, the offset amount, with the frequency values. Right, if I look at the results, let's see, random range. Okay, so for instance, my lowest frequency is 159. Well, here is 159.4, and here it's 159.2, and my second frequency is 48. And the second one is 48.0, whereas the first one was 48.2. So as you can see, these are very small differences, very small nudgings of the signals. Right, there we go. All right, so how do we add these together, though? That is the question. So how do I add these together? Well, I can't use the plus object because that would actually add the values in the signals together. And I want to combine the signals together into a larger multi-channel object. And would you know, the name of the object is mc.combine_tilde. And by default, it's going to combine 2 signals. Just to be sure, I can give it the argument 2 to tell it to combine 2 signals together into a larger multi-channel signal, right? So I can do it like this. I'm sending my offsetted frequencies as well as the original frequencies, and the result is 18 channels, right? 18 channels. Each channel containing one of the frequencies or one of the offset frequencies all together. Now, doing this requires me to change a few things in my algorithm, though. So instead of sending, and we have to maybe make some more space here to make sure that things don't get squished too much. There we go. So instead of sending my 9 original frequencies to be divided from the fundamental frequency to figure out the release, I should send this new combined amount. Right, but other than that, I think the result is the same. All of these objects are going to know they're now dealing with 18 channels, and it's still going to be mixed down to 2 channels. So it's all nice, it's all beautiful in the end. Okay, so here's the moment of truth. How is this new version going to sound? Can you hear it? Can you hear the lower frequencies beating? You can hear this periodic oscillation between them. And this is as close as we can get to a bell sound without adding a few more small details. And now we have a lot of parameters we can change. We can change the offset of the frequency ratio. We can even make it higher. We can make it crazy high. We can generate new offset values for our frequencies. And we can of course change the fundamental frequency. Okay, so now let's add some bells and whistles to it before we call this a video, because one thing, of course, I want reverb in this. I want this bell sound to actually ring, and there's only so much I can do within simple ADSR envelope. So I'm going to use an abstraction in Max called Yaffer 3. I think they released Yaffer 3. I believe this stands for yet another free reverb. So it's a free reverb abstraction. This guy takes in a single signal and it sends out two signals, a reverb signal. So I'm going to change MC Mixdown's argument to 1. I'm going to change MC Unpack's argument to 1. I'm going to plug this into Yaffer 3, and I'm going to get the outlets here. And by default, we should have a heavily reverbed sound. Nice, maybe a bit too reverbed. All right, well, there are all these inlets, and the first one is the size, the second one is the decay time, the third one is the damping of the reverb. So what we can do is to create live.dial and plug its first inlet into each of these, plug its outlet into the inlets of the corresponding inlets of the object. My brain is melting from approximating bells. All right, and then I can change, let's say, the size, the decay time, the damping, and the diffusion. I'm kind of putting semi-random values in here, but now I can have a more controlled reverb. And if I really want, I can try to make a dry wet knob, right? I can maybe add some of the original signal and some of the reverb signal. And there is again an abstraction we can use for this called, let's see, M for L, I believe, so short for max for live, bell2, balance two signals, mix them together, create mixtures of two signals. And the first two inlets here corresponds to the dry signal, or the first signal you want to mix. The third and the fourth inlets are the signals of the other signal you want to mix, the left and right channels of the other signal, and the two outlets are left and right channels of the output. The final inlet is the amount of mixture expressed in a value between 0 and 100. So we can create another live.dial, right click on it, go to prototype, go to amount, right click on the dial, go to prototype, go to amount, and we get this nice percentage indicator which we can hook up to this guy right here. And now I can have a dry wet amount in my signal. So finer control over everything. Increased a bit more. Beautiful. And you could more or less convince me that this is a bell. Maybe we can lower the offsets a bit more in order to have a stronger approximation of a bell. I don't know. Like we can play around with this all day if we want to. There we go. Now that's a nice bell sound. And here we did it. We have implemented Risset's algorithm to approximate a bell sound by just adding a bunch of sine waves together and be clever about the way we organize information about these sine waves, their frequencies, their amplitudes, and the ratios between the frequencies and the amplitudes. And of course, that's just a starting point, right? As I've said in the very beginning, the idea here is to figure out how this works instead of using a bell sample, so that you can modify, so that you can add your own variations on it. And there are a lot of moving parts here, right? So there are all these offset values. So what if you try extreme offset values? What if you don't generate random values, but generate something else? What if you went to the reference tab of mc.sig and looked at all the other messages here and see how else you can generate values? What if you used different frequency ratios? What if you turned this into an instrument, right? What if you figured out random MIDI notes and play around with that? I don't know. I mean, there's a lot you can do with this, and I think the less like a bell this sounds, the more interesting it is, the more it is your sound. But that is just my opinion. In any case, enjoy creating bell sounds, enjoy creating unbell-like sounds, and thank you for watching.